Morning everyone, morning Tanishka. So part 2 of Chemistry 2. Last lesson I think we started looking, or we looked at the ionic bonding. We looked at why or how ionic bonding works. We looked at sort of some of the fundamentals, and we carried on looking at this idea of the periodic table and using it as a cheat sheet. Well done to those of you who have sent through sort of some pictures of trying to make some of the organic molecules and making sure that you've got the electron configurations correct, and you had to go out using the sentences to describe what's going on as well. That was really good to see. So we'll start with a quick recap. We're then going to go on, we'll finish off just going back over the properties of ionic compounds, and then we're going to move on and have a look at covalent today. So let's make a start. Now remember that elements react in order to try and get to a full outer shell. So everything we're trying to do is to try and get 8 electrons into that outer shell, unless it's the first shell. Remember, the first shell only holds 2 electrons, but otherwise we're going to be looking at 8. And they're going to lose that either by losing and gaining, so the transfer of electrons if we're looking at ionic bonds, or in the case of covalent bonds or covalent molecules, we're going to be looking at sharing. And we're going to have a look at how that works today. We also said that our sort of fundamental idea here with all the way through is that opposite charges attract. So we're just going to put that down because actually we need to make sure that whenever we're coming back to look at any of these, that is the key point that we're actually trying to get our heads around. Okay, where are the charges? What's going on? Because a lot of the time that will help us to explain the properties of these compounds. Now, we said yesterday that when we were looking at ionic, we said ionic was always going to be between a metal and a non-metal. We said that the metals always lose electrons to become positive cations. We said that if we know that group 1, morning Amy, we said that group 1 loses 1 electron, group 2 loses 2, and so on. Until we get to the non-metals, and then group 7 gains 1, group 6 gains 2. We looked at the charges they formed as well, and we said we can use the periodic table to calculate that. We then said yesterday that actually once they join, it's a bit like, and let me just grab where I put the straw, I put them in, that one. We said that actually when they react, afterwards we're left with these sort of opposite charges. So it's very similar to sort of magnets really, in the fact that actually they will sit there and they'll clump together and they'll form our ionic compound. So they're all joined together. We know that with magnets we get north and south, and they'll be attracting. And if we're looking at ionic compounds, we've got the positive cations, we've got the negative anions, and they're all joining together in that way. In order for them to try and melt, in other words, go from a solid like this to some form of liquid, where actually they're sliding past each other, and are turning into a fluid, we've actually got to give them enough energy to break some of these bonds or to start overcoming some of these. And what we're trying to do is we're trying to heat them up to the point where the atoms are going to start vibrating, and as they start vibrating, eventually we're going to start getting movement in these bonds. And if we give enough energy, and I'm not going to do it here because I'll end up throwing one through my monitor, but if we give them enough energy, we can actually even turn them into a gas as some of them break away. So that's what we're looking at. When we're looking at melting points and we're looking at boiling points, we're trying to give them enough energy to overcome the forces or the bonding between those atoms, if it's a molecule, or between the molecules, depending on what we're trying to achieve. So all the way through this, that's what we're going to be talking about. Now, we said that when we look at ionic compounds, we said that actually we usually draw them out in the typical way to the way we draw our standard sort of key stage 2 and 3 solid diagram. Okay, so we have them generally fairly structured. It is a giant lattice. So they're huge molecules, these. Each grain of salt you look at is going to be 1 molecule. So there we're not looking at small molecules. Most of these are going to be giant lattices. And they're going to all have opposite charges. Similar to that. Now, if you have a look at the three-dimensional molecules, We notice that they're not all jammed together like that. We can start putting bond structures in. I'm not going to worry too much about this now. I'll probably come back to that maybe Friday, maybe next week. We shall see how it goes. But we've got all of these opposite charges and they're all stuck together. We said that actually they're going to have high melting and boiling points. So melting point and boiling point. And in an exam, we want to put down because. So I'm just going to do the because in a different colour. So high melting and boiling point because we have strong, and I can either say intramolecular bonds, or we can say strong or forces, or I can say strong ionic bonds, which take lots of energy to break. So in an exam, that's what we're trying to get our heads around. We've got the property, but how does the structure help us explain that property? And that's what we're trying to do to get good as chemists and good as scientists. Because just memorising they've got high melting and boiling point, that's really only foundation. And as we've said before, the more we can understand, the less we actually have to remember. So what we're trying to achieve here is if we can understand the properties, so in this case, a strong ionic bonds, loads of energy needed to break. We know that to provide that energy, we've got to heat them up. So in other words, we're going to have a really high melting point and boiling point. So that's them making those links. With these, we notice that these solids do not conduct electricity. And they're pretty bad conductors of heat as well. Now, if you look at the definition for electricity, we're usually looking at the movement of electrons or the movement of ions. So we can put that in here as well, just as a bit of a recap. I know it's physics, but actually we do need to understand it here as well. So for this, we're looking at the movement of electrons or ions. Now, this is a solid, which means the particles are not moving around. So if they're not moving around, therefore we can't have anything conducting. There's no free electrons. So in other words, there is no form of charge that can move through this structure. So the solids don't conduct. However, if we can melt it or dissolve it, so we're going to look at liquids, or we're going to look at aqueous, so in other words, a solution, then the ions can now move. So these will conduct. So again, I'm just going to put the reason for it in red. So liquids or aqueous, they will conduct because the ions, and I'll just put charges in brackets, can now move and carry a current. So that's quite important. The solids don't conduct, and we can see this with experiments in a lab. I can't do it here, but actually if we have two electrodes going into a salt compound that's a solid, and we have it attached to an ammeter or a voltmeter, it will read 0. But if we put a Bunsen burner underneath that, and the one we normally use because it's got a low boiling point-ish, or low melting point, is lead bromide, low in comparison to some of the others, then as soon as it starts turning into a liquid, and we reach that transition point, we see the current starts flowing very, very fast. So it's quite important that we get our heads around that. Solids don't conduct, but liquid or solutions do, because it means the ions are free to move and they're free to carry that charge. Yeah, so hopefully that makes sense in terms of the sort of ionic compounds. And we're going to be coming back and looking at these properties with small covalent, giant covalent, and with metallic compounds as well. But that's sort of the basics with the ionic that we've got to get our heads around, got to make sure we fully understand. Now, covalent. So a covalent bond is between a non-metal and a non-metal. We said that ionic was a metal and a non-metal, but a covalent is a non-metal and a non-metal. Now, we'll just change that across just in case anyone messages on that. Brilliant. So there are two sort of molecules that we look at, which is the small covalent and the giant covalent. However, it doesn't make a great deal of difference in terms of the actual bond itself. What makes a difference is when we're looking at the properties of the molecules. So, with a covalent bond, we are looking at the sharing of electrons. And we're sharing to try and get a full outer shell on both atoms. Now notice I'm not going to use the word ions when we're looking at a covalent molecule. We're not exchanging electrons, so there is no change in charge. But we are looking at sharing of electrons. And when we share that electron, the electron gets counted for both atoms at the same time. And I think that's where a lot of students seem to struggle to get their heads around. The electrons in the middle, and we'll draw some of these out in a minute, we've got quite a few to have a look at. The electrons in the middle, they get counted for both atoms. So we're always trying to work out how to get to a full outer shell, depending on what the element is. Covalent bonds are very, very strong. Now, we may have weak forces between the molecules, and this is where it's really, really important. If you're going to use the word intermolecular and intramolecular, this is probably the most important place not to make mistakes. The covalent bond is going to be intramolecular. So that is inside the molecule. However, when we look at a lot of the smaller molecules, they are often intermolecular forces between them, but they still have strong intramolecular. Now, if that's going over your head and you're getting a bit confused, that's fine. Talk about strong covalent bonds and weak forces between molecules, and you won't make mistakes that way. But if you want to try and use those words properly, intermolecular is between molecules, but the covalent bond is intramolecular because it's inside. But don't feel you have to. Now, let's look at probably the simplest one. And what I want to show you is there are sort of 2 or 3 different ways of drawing covalent molecules. There's one way that you have to be able to do, but you need to recognise the others in case it comes up in the exam. Now, I'm going to start off, I'm going to draw the molecule to start with. We're going to look at hydrogen. So we know with hydrogen has 1 electron in the outer shell. However, this first shell, or this first energy level, can only hold 2 electrons. So it only needs 1 more electron. So it's going to form 1 bond. Now, we're going to look at ways of using the periodic table to make our lives easier with this. But for the moment, we're looking at the fact that it's got 1 electron in the outer shell. The first shell can only hold 2 electrons, so it only needs 1 more. So that's 1 bond. Now, the quick way that we draw these is with a line. And this line represents 1 covalent bond. Okay? So if I've got 2 bonds, I would have 2 lines. And we'll have a look at that in a moment. So if I want to draw this out, let's just do 1 circle. Then what I need to have, and another circle, I need to have an overlap in these shells in order for them to react. So let me just see if I can move this over like that. So that's what we're trying to achieve. We need to have this overlap. So I've got my hydrogen. As I did with Ionic, I'm only worried about outer shells, although like I said with hydrogen, we've only got 1 shell, but I'm not worried about the nucleus at all. So I'm going to put the 1 electron for each of the hydrogen atoms in the middle here to show they're shared. Now, this counts for both hydrogens at the same time. So this one here has 1, 2 electrons. This one here has 1, 2 electrons. So they both have a full outer shell. The other way of showing these, and this is the 3rd type of diagram, is we can actually draw them with a dot and cross without putting the orbitals in. And again, that's perfectly fine, but this one here is the preferred method for showing these. Okay? Now, let's go and have a look at another molecule. And I'm going to draw quite a few of these today. You need to make sure you can understand them. All of the ones I'm going to show you need to be able to do. So ideally, you'll be able to work them out as you go along in the exam, and that's the sort of skills I'm going to try and give you. But if not, then you do just need to remember them. But realistically, we don't want to just be remembering facts. We want to understand how we got there, because the last thing we want in an exam is to have those sort of brain blanks and start panicking and not being able to remember it, and then not being able to work it out as well. So let's have a look at oxygen, and we'll see how oxygen works. Now, oxygen is in group 6. All group 6 elements will form 2 covalent bonds. So this is where we're going to start using the periodic table to aid our thinking. If you've got the cheat sheet from Chemistry 1, it's on my website and it's on the Google Classroom. Have a look at that, because I've put all of these comments in there, and I'll re-upload it to this lesson a bit later on as well. So we have 6 electrons in the outer shell. So to get to 8, we need 2 more electrons. So therefore it's going to form 2 covalent bonds. So if I'm going to draw this out, there's only 2 atoms. So both those bonds are going to be between those 2 atoms. So let me draw this out in terms of the circles again. There we go. And we'll overlap them as we did before. Now, what I find easiest with this is I find it easiest to put in the pairs of electrons here first. So if I know the group it's in, I know it's going to form 2 bonds, I'm going to put these in first of all. So there's my 2 pairs, 1 for each bond. Now I know that oxygen had 6 electrons in total to start with. I've put 2 in the middle. That means it's going to get left with 4 more. Because that means 1, 2, 3, 4 is what I started with. Okay. So, yeah, so there. So I've got the electrons in. Now if we count them up, remember these electrons in the middle count for both atoms at the same time. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So they've now both got full shells. And if I want to draw it in the other method, I find this way gets a bit messy, but it's quicker, I suppose, in terms of not drawing out all the shells. But it is a method. This one is the preferred one that we need to get our heads around. It doesn't make any difference whether you want to draw them next to each other or in a row going down. I like drawing them this way because I think it represents the bond, and it helps for us to try and get our heads around that. But it wouldn't be a problem at all if we wanted to draw them out. Let's just do that now. So we could also draw it, and lots of people teach it that way. There's nothing wrong with that in any way, shape or form. It's whatever you find most comfortable with that you're going to make the least mistakes with. So both of those two would work. Okay. So we've looked at hydrogen, which is sort of... technically, in this case, we'd be considering it group 7 because it forms 1 bond, and all of group 7 forms 1 covalent bond. So we can put our sort of up here, group 7, 1 covalent bond. We've got group 6, always forms 2 covalent bonds. Group 5 is 3, and group 4 forms 4 covalent bonds. So I'm going to be using this as just a check as we're going through. In this case, like I said, we're considering hydrogen in group 7 because it forms 1 bond. So let's have a quick look at group 5. And then we'll start having a look at some compounds rather than just molecules. Remember the difference, a compound has 2 or more different elements. Now, group 5 then. So we're going to do nitrogen. So as we did before, we know it's going to have 5 electrons in the outer shell. By the way, once we've got our heads around what's going on, we don't need to write this out all the time. Personally, I look straight at the periodic table, go, it's in group 5, it's going to form 3 bonds. But it's worth going through this lots of times until you're sick to death and bored with it, because once you get to that stage, you're going to remember it. So, 5 electrons in the outer shell. Needs 3 more electrons to get to a full outer shell. So therefore, it's going to form 3 covalent bonds. So let's just copy that. There we go. So I'm going to put the bonds in first. I know it's going to form 3, and I'm going to get 2 atoms here, so it's actually really nice and simple. 1 bond, 2 bonds, 3 bonds. Each nitrogen started off with 5 electrons, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So what we've just done is that. In terms of going back to our sort of key point then of opposite charges always attract, hopefully you've sort of had a bit of a think and you can see, but what we've got is this positive nuclei here and these negative electrons here. Positive nuclei, negative electrons. So we've got the opposite charges attracting between this positive nuclei and negative electrons. And that forms a very, very strong bond. And we'll come back to that a bit later on. If you want me to slow down or go through any of this again, please just type it in the comments and let me know. Otherwise, we're going to carry on and we're going to have a look at our first compound. So I'm going to draw methane. So methane is CH4. So I'm going to look at this as 2 separate atoms to start with. So we'll take carbon. Carbon's in group 4. It needs 4 electrons to get to an outer shell. So it's going to form 4 covalent bonds. I've then got hydrogen. Each hydrogen only forms 1 covalent bond. But I've got 4 of them. So it's going to look like this. Each hydrogen has 1 bond. And my carbon is forming 4 bonds in total. So let's draw this out. One. 2. 3. 4. So we'll put those in. I've got carbon, hydrogen, 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 and hydrogen. There we go. So I've just drawn those bonds in. And if we have a look at it, the carbon now has 8 electrons around it. Each hydrogen has 2, but hydrogen only needs to have 2 because it's only got that first energy shell with electrons in. Remember, all the other energy levels still exist, but they're not occupied by electrons. So we've got those, we've got 2 for each of the hydrogens, 8 for the carbon. Okay, which we'll have a look at next. Let's do carbon dioxide. So, same way as before, carbon is going to form 4 covalent bonds. Each oxygen's in group 6, so only needs to form 2 covalent bonds. So we're going to need 2 oxygens to fill the 4. And what we end up forming is a molecule that looks like that. So let's draw it out. So we should have carbon, oxygen, oxygen. 2 bonds, so we're going to have 2 pairs of electrons. Now, the carbon only had 4 electrons to start with, so I've used those 4 electrons up, so I don't need to draw any more electrons around the carbon. But each of the oxygens, because it's in group 6, had 6 electrons to start with. So I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So when you're looking at this one now, if we count all these up, for the oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. And the other oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So they all have that full outer shell. Right, we're going to keep going for a minute. If you've got questions, again, just stop me. Feel free to ask. If there's anything you're not too sure about, or I'm going a bit quick, or if you want me to go back over any of these molecules again, do just ask, because it's really important that you can actually do these. So I've got a few more that I want to go through, and I'll do a few more complicated ones. And then we'll have a look at some of the properties. Okay, yeah, absolutely, Tanisha. I'm more than happy to go through this. So, if we just have a look... Where did I do that one? We'll just go back through this one again. So methane is CH4, and it's one of the ones that you need to know the formula for. It also comes up later on when you look at some of the organic chemistry and when we look at oils as well. So it's a type of alkane. We know that we've got 1 carbon and 4 hydrogen. Now, if I go and have a look at my cheat sheet, because again, as far as I'm concerned, the periodic table is just helping us to cheat, because if we can learn to use it properly, we've got the answers on there. I know that any element in group 7 will have 7 electrons in the outer shell. Okay, no problems. 7 electrons in the outer shell, so it only needs to form 1 bond. And that works our way down. So, any element in group 4, that should be a G, not a C, will have 4 electrons in the outer shell, so it only needs to form 4 more. So it forms 4 bonds. Now, if we have a look at carbon dioxide, carbon is in group 4, so it needs to form 4 bonds. It needs 4 more electrons. Oxygen is in group 6, so only needs to have 2 bonds per oxygen. So what we're going to do is, if you notice around this one, the carbon is forming 4 bonds. Each one of these is going to allow it to share 1 extra electron. So if it started off with 4 electrons, it's now got 5, 6, 7, 8, because it's sharing 1 more per bond. Each of the oxygens started off with 6 electrons, and it needs 2 more. So if we start off with 6, then actually it's going to get 1 more for each of the bonds it forms. So we've got 6, 7, and 8. Now, whether you start off with this way or whether you start off with this way, it doesn't actually matter. And sometimes what you'll do is you'll end up drawing a molecule, particularly for some of the bigger organic molecules, you'll end up drawing a molecule and going, that doesn't work. And that's absolutely fine, because we can look at drawing it in another way. And some molecules, there might be more than one structure. If we know the name, we can work the structure out. But for these basic ones, I would suggest working out the number of bonds, and a bit like Lego, working out how many bits you can fit around a particular sort of Lego piece. It's exactly the same thing here. So a bit of trial and error with it. So let's go through some more, and then we'll see how you feel about that afterwards. Right, let's have a look at water. So we've got, again, 2 different elements. We have oxygen, group 6, so it's going to form 2 covalent bonds. Hydrogen, we said, in terms of covalent molecules, we consider as group 7, so it only forms 1 covalent bond. If you notice, I've got 2 hydrogens and 1 oxygen. So what we're going to form is a molecule that looks like this. I will talk about the shape of these a little bit later on towards the end. Why I've drawn it as a bench shape rather than linear, we'll come back to that later, okay? It's slightly more advanced, and what I don't want to do is lose everybody now. So we'll just look at the diagram for this to start with. So we know that oxygen had 6, so it's going to gain 1 extra for each of the bonds, and hydrogen only needs to gain 1 extra electron, and it does that by sharing in this bond. So let's draw out. There's an oxygen. We'll put our hydrogen in. Hydrogen we generally do draw much smaller. I mean, all of the atoms are different sizes. But let's face it, when we're looking at hydrogen, it's only got one shell. So it makes sense to draw it a little bit smaller. So I'm going to draw my bonds in first. There they are. Hydrogen we're done with. Got 2 electrons in the outer shell, so the outer shell is full. We know that oxygen started off with 6 electrons, but I've only drawn 2 in so far. So I need to draw the other 2 in there. And we can start to see a little bit more about why I've drawn it the shape it is up here. So 1, 2, 3, 4, 5, 6, and then it's shared 7, 8 to give us this structure here. And feel free to go through and practice these later on. Try and draw them out, come back to the video, come back to the notes and see whether you've got them right. And drop me some questions if you're not sure. Right, ammonia. So, nitrogen, group 5, 3 bonds. Hydrogen, as we've said, 1 covalent bond. So, I'm looking at having 3 bonds with a hydrogen on each. And we're going to get to a shape something like that. So let's draw that out. Come on. There we go. Not working today. Let's try that again. Always happens when you're trying to save time on it. No. There we go. So, draw my circles out. And let's have a look. Now, as I've done all the way through, I'm going to put the bonds in first. The nitrogen starts off with 5 electrons, but I've only drawn 3 in so far, so I'm going to put the other 2 in to get me up to 5. And I suppose that's probably one of the biggest areas people make mistakes with on this one. A lot of the time they get the bonds correct, but they often miscalculate when they're putting in the additional electrons at the end. And you often end up with atoms with sort of 10 electrons, which don't really exist like that at GCSE. So it's really important that we go through and we sort of work out these calculations properly. So I put my 3 electrons in for the nitrogen, and I know it starts out with 5, so I've only got to put 2 more in to get up to 5. And now if we count them out, we should have our 2, 4, 6, and our 8 electrons. So it's that little attention to detail that's going to make a massive difference when you're sort of going through, you're working out the grades in the exam on these ones. Okay. Going to go for something a little bit more difficult now. So let's have a look at ethane. So again, ethane is a molecule that you should be able to draw. It's one that will come up later on in the unit, so it doesn't come up in chemistry 2, but it does come up when we start looking at organic chemistry later on. But it shouldn't make a difference, and it's slightly scarier looking. The process is going to be the same. What we might have to do with, though, is play around with our sort of virtual Lego blocks, our atoms here, to try and work out which configuration is going to allow us to have all of the atoms joined up and all of the bonds filled. And I'll show you what I mean. So we know we've got 2 carbons, and each carbon is going to form 4 covalent bonds. I've then got 6 hydrogen, and each one is going to form 1 covalent bond. Now, if we were to just draw these out, and sometimes it's quite useful to draw these out on bits of paper and cut them up, and then try and sort of rearrange them, I'm then going to have sort of 6 hydrogen like that. So it doesn't make any difference how we sort of rearrange, join these together. If I was to put a hydrogen in the middle, I couldn't join the other carbon on, because let me just show you what I mean. If I put a hydrogen here, hydrogen only forms 1 bond. so therefore we can't connect with this carbon here. So it is a bit of trial and error. And if you're making mistakes, that's not a problem. Those of you that I teach will know that actually if you're not making mistakes, either I'm not doing my job properly and I'm not actually asking questions that are difficult enough, or you're not trying. Because it's perfectly normal to make mistakes on this and get it wrong. I think just a few of you struggle to make your work, it makes your work look a little bit messier because you haven't got the perfect answer down every time. And I'm going to say that just to see if anyone comes online and comments. But yeah, so don't be afraid about getting mistakes. Don't be afraid about copying things out. And if you have done something and made a mistake, that's brilliant. But put an annotation on your work to say why it's wrong. So the next time you can see the thought process that you went through in order to be able to get there so you don't go through it again. But actually leave the mistake on there as a progress that you've learnt so that you can carry on learning from it in the future. And that'd be brilliant. Now, let's have a look at the actual molecule then. So the molecule is going to look like this. So there is my ethane molecule. Okay, there is a molecule, Tanishka, where you will have a triple bond to the carbon. Oh, I see what you mean. No, I see what you mean. Yeah, this is the molecule that we're going to form. We can form triple bonds with carbon, and we'll have a look at some of those a little bit later on. But yeah, you're right. This is what we're looking at forming here. So let me draw this out then. There we go. So I've got the first one. I've got the two carbons in. Now let's draw a hydrogen. So I put all my orbits in. Now we'll just put these in. So we've got carbon, carbon. Okay. And now let's work on the bonds. So remember, each one of these bonds is going to be a pair of electrons. So I'm going to put those in first. Ooh. And we should end up with a molecule looking like that. The thing is, because there's lots of dots and crosses, it looks more complicated. And I think a lot of students get to a stage and they go, oh, I don't like that. That looks really complicated. But if you go through with a bit of practice and you sort of take it fairly logically and you sort of work through the sequences and you don't try and jump straight in at the end, but you break it down into the smaller tasks, how many bonds, how is this going to fit together? I personally find it easier to draw them out like this, but it's not a problem going here. All you've got to do is make sure that you count up the electrons afterwards and you don't sort of put any sort of spurious extra ones in that didn't exist, or you've got ones that aren't actually in a bond and then you start getting confused. You go, well, actually, I thought there was a bond there and it's not. So just go through and practice and don't be afraid to make mistakes on these. Now, we've drawn ethane. Let me show you ethene because it's got a slightly different configuration. So ethene is that. So notice I've still got two carbons, but I've only got 4 hydrogen. Now, if we were to draw it out the same way, and I tell you what, let's do that now. Before we actually go through and look at the bonding structure, let's just go through and draw this out. Let's just move over that. There we go. So let's just go and draw this out as we did before, and then we will sort of work out one of the problems we've got. So I'm going to put in the electrons. So hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen. Now hopefully when you're looking at that, you can start seeing the problem that I've got. Each of the hydrogens is absolutely fine. They've got a full outer shell. But if you count up the electrons for the carbons now, I've got 1, 2, 3, 4, 5, 6 for this one. 1, 2, 3, 4, 5, 6 for this one. And actually, when we draw this out, I've ended up with that. So each of my carbons only has 3 bonds, which means I'm not meeting the rule that we said that group 4 always has to form 4 bonds. So in actual fact, what you find with this one is we end up with a double bond between the carbons to make it work. And that way, they still end up with a full outer shell, and all of our rules that we've come up with before now work absolutely fine. Okay? So, again, let me know if that doesn't make sense, but we've made sure that we've fulfilled the rules that each carbon has 4 bonds. Each of the hydrogen has 1, and they now all have a full outer shell. 2, 4, 6, 8. 2, 4, 6, and 8. Now, the beauty about doing this with organic molecules, I say beauty, you guys are going to be looking at me like, oh, he's absolutely weird. What does he mean beauty about this? Yeah, I'm a bit of chemistry geek. I quite like things like this. I quite like it when things are really logical. And actually, once you see it, you're just following the same rules each time. And it is just problem solving. It's a bit like doing a good crossword or a puzzle or whatever. It's just that once you get your head around the logic behind it and you can do it, it's just solving a problem. So don't be afraid that you can't do it. It does just come down to practice. Now, I want to do one more, I think. I can do these all day. There's lots of different scenarios for these. But I'm going to do one more. And then I need to talk about the properties of some of these molecules. So I'm going to go for another molecule based on these. And I'm going to go with ethanol. So ethanol is sort of the alcohol that is in drinks. It's alcohol that we use for cleaning products, in hand gels. And it's got the formula of C2H6O. That's one way of writing it anyway. There is another way, but we'll come back to that. So, all of a sudden, my puzzle has got even harder. I've got 2 carbons, and we know that's 4 bonds. I've got 6 hydrogen, and that's 1 bond per hydrogen. But I've got this oxygen in there now as well, which forms 2 bonds. And students seem to look at this and they're going, well, how does that work? And actually, there are different ways of doing this. So, as I said before, if we're looking at ethanol, there is only one structure with it, so the name will often help us. So if you come up with another way of drawing this out, don't worry about it too much, because I haven't given you the other way of writing the formula out at the moment, and I'll do that in a moment. I don't mind if you get a different molecule as long as it meets all of the criteria we've said, that each carbon must have 4 bonds, each hydrogen must have 1, and each oxygen must have 2. Okay? So, let's have a look at how this works. We know for a fact that we cannot put oxygen in the middle of, hydrogen in the middle of this molecule, because it only forms 1 bond, which means we wouldn't be able to connect the carbons and the oxygens to each other. So, come on, there we go. Right, so what we've got here, and I'll do the correct way of doing this one, we've got carbon, and we've got an oxygen. So I'm going to start off putting 1 bond in for each. Okay? So I've got a bond between the carbon, bond between the oxygen. Now oxygen can only form 1 bond. So let's have a quick look at this. Sorry, what am I saying? Oxygen can only form 2 bonds. And it's already formed 1. So therefore, it's going to have a hydrogen there. Ah, there's a cross as well. So my oxygen has 2 bonds. My hydrogen has 1. So actually, these 2 now fulfill the criteria. What I'm left with is 5 more hydrogens. So let's just see how this is going to work. So there's my 5 hydrogen. And there we go. Now, let's just count up to make sure. Okay, Tanisha, in terms of the crosses and dots, I'm only using crosses and dots to work out, to make, so you can show the difference, or to help make it a bit easier to understand where they're coming from. There isn't any general criteria that this element must have a cross and this one has a dot. So generally what I do is I work out the bonds that are going to be formed, and then I work out whether I need to put any other electrons in. So if you notice at the moment, the oxygen does not have a full outer shell. So I always put the bonds in first, and then I go through and double check what else I need to do. So if you have a look, all of the hydrogens have a pair of electrons, so they have 1 bond. So in other words, they have a full outer shell. If we look at the carbons, I've got 2, 4, 6, 8, 2, 4, 6, 8 electrons. Both the carbons have a full outer shell, so they're done. And they both have 4 bonds, which meet this criteria up here. But the oxygen's only got 4 electrons at the moment, and it needs to have 8. And if you notice, I've only used 2 up of its own that it started with, and it started off with 6 because it's in group 6. So I'm going to put those in, and that then is done. There is another way of doing this one. Now, this takes a bit longer to do, but if you've got time at home and you want to start seeing how things work, what we can do is you can actually... Oh, hang on. You can actually draw the molecules out to start with, and this is exactly what I'm going to do. So I'm just going to duplicate this. I'm not actually sure if I can rotate round, so we'll see how this works in a minute with this particular software. It'd be really cool if I can rotate it, but I've got a sneaky suspicion I think I won't be able to. So, we've done that one. I'm going to draw my carbon. We know that carbon starts off with 4 electrons. So, and I've got 2 of those. And I need to draw an oxygen as well. I'm just going to do them all as crosses for the moment. It makes no difference. Oh, let's do that. Okay, so I've just drawn them all out separately. So the next thing I can try and do is to try and join them up and overlap them. So let's just see how this works. I'm going to overlap that one there. I'm going to move that one to there. Now, the problem is, if I can't rotate these in any way, it's going to start getting a little bit difficult to see what's going on. But I'm going to put one of them there. Yeah, I've got no option to rotate them. Okay, bear with me. Let me just get rid of the electrons. If you're doing this on paper, it's much easier, because if you do it on paper, you can just rotate the paper around. So I'm going to put that one there. Oh, it's not working. Anyway, you get the idea. So literally what you can do is with bits of paper, you can draw all the electrons in that you would normally have. And then you can literally, if you do it on tracing paper, it's even better because you can cut them out and then you can move them around and overlap them until you get your molecule work, your molecule done. So with this particular whiteboard, if I could have rotated the molecules around, I would have rotated them around until I make sure I had all of these filled in. But don't get too hung up on which one needs to be a dot, which one needs to be a cross. If you're really not sure, just do them all as crosses. They are called dot and cross diagrams, so for the simpler ones, it's worth doing. Okay? But that should just be another way of drawing the same thing. Let me just get rid of that so I can actually use that part of the canvas. Don't be afraid to draw them out and then move them around and overlap. Okay? Right. Let's just move on and have a look at some of the properties. Now, what we've said when we're going through this is we said that the covalent bond is very, very strong. And it is really strong. It's massively strong. It's one of the reasons why when we look at some of the bigger molecules later on, like diamond, and we'll do that on Friday, diamond is one of the hardest substances we know of because the covalent bond is really strong. But if we take something like CO2, we've got this molecule here. Okay, we've got a molecule like this, we've got loads of them floating around. Now, what we have is we have these really strong intramolecular bonds or forces. So in this case, bonds, and it's a covalent bond. In between them, though, we have weak intermolecular forces. And remember when we were looking at the properties, when we looked at the ionic bonding, we said that actually ionic bonding has a high melting and boiling point because it has strong ionic bonds which take lots of energy to break. Well, if we look at the forces between the molecules, if these are going to be weak, that means very little energy is needed to break. So therefore, it's going to have a very low melting point and boiling point. Not random. How do you know which element will follow which bond? What do you mean? So in terms of with this molecule, I could have tried putting the oxygen in between them, and I would have got a different molecule. Ethanol, the actual way we normally write ethanol. Come on, not working. The way we normally write ethanol would be C2H5OH to show that we got the OH on the end. I deliberately didn't do that way because actually I wanted you to have a go. If you like, Tanishka, what I'll do is I'll give you some other molecules to have a go at drawing out, and you can post some pictures up and see if they work. So I'll put them on this on these notes at the end of this lesson, okay? And you can have a go at drawing them out before Friday and seeing if it works. Okay, so we said that they have very weak intermolecular forces. So because they're weak, very little energy needed to break. So they've got low melting and boiling points. And if you think about a lot of the molecules we've looked at, oxygen's a gas at room temperature, it's a gas now. Nitrogen's the same, carbon dioxide's the same, ammonia, methane, all of these are gases at room temperature. Water is an exception. I'll talk about water in just a moment because there's something peculiar going on with water which gives it a higher melting point and boiling point than it should have. But it's also the reason that we've actually got life on Earth. So it's actually quite cool. So we'll have a look at that in a moment. But yeah, so we've got weak intermolecular forces, virtually very little energy needed to break. In order to try and turn a lot of these to liquids, we've got to sort of drop the temperatures below 100 degrees Celsius. Some of them much, much lower than that as well. There are no ions or delocalized electrons. So remember we said that delocalized just means free moving. So electrons that can move through the structure. So this will not conduct. Okay, it's not going to conduct electricity in any way, shape or form. And that's pretty much it for small covalent molecules. Now, I just said I'd talk about water. This is slightly higher level, but most of you guys are pretty good with this. So I'll just put it down and I'll leave that there, and then I'll just give you a few more molecules over here to draw out if you want to have a go at home. Now, if we look at water, let's just draw some random water molecules out. I don't know, let's just do another one like that. We'll see how it goes. Now, if you remember, if we have a look at, where's my water molecule gone? There it is. If you remember water, we've got this sort of bent shape here. I've got these electrons sticking out here. And I've got these lone electrons at the top. Now that's really quite important. So, if we look at the water molecule, what we've got is we've got this oxygen with these electrons here. We've then got this bond here with two more electrons. And we've got these hydrogens stuck out the end. And if you look at the structure of a hydrogen, it is a single proton with an electron whizzing around the outside. Well, if that electron is here, all I'm left with on the end is a single proton stuck out the bottom of the water molecule. So let me just draw that in for a moment. So I've got this single proton here, and I've got these very negative electrons at the top. Now, what that means is the bottom of every water molecule, if you call the hydrogen the bottom, is positive, and the top of it's going to be negative. So we end up with this sort of force of attraction, and this again is an intermolecular force. And we call this a hydrogen bond. Now, it's not a full bond, but it is a force of attraction between the hydrogen, this proton stuck at the bottom, and these negative electrons. And because that force of attraction is higher, what this now means is more energy is needed to break the bond or the force, which means the boiling point goes from, say, minus 120, it brings it up to 0 degrees Celsius, which we know of as the freezing point of ice, and it boils at 100. So it means that actually water on Earth and anywhere else is a liquid at the temperatures that we live at. If we didn't have this force, this hydrogen bonding, we would not have liquid water on Earth, which means there would be no life, we wouldn't exist, and none of this would be happening as it is now. And it gives other properties as well. It enables trees to draw water up through transpiration, which you should remember through when we looked at biology 2. We went through transpiration then. So this sort of one science concept, this one idea, this one force between the water molecules is the reason that we have life and that everything is actually surviving as it is now. So that's pretty much me done. So I said if you wanted to have a go yourself at drawing some of these out. So I'll just put those in a separate box. And we'll just say, right, have a go. So have a go at doing hydrogen chloride, which is a gas. We're looking at the gas. We're not looking at the acid. Have a go at doing methanol. So methanol is CH3OH, or you can also draw it out CH4O in the same way as I did the ethanol. Have a go at doing, what other one should we do? Let's do propane. So propane is C3H8. We've also got propene, which is C3H6. And we can make them more difficult as well. There's other options as well. So I could do some more, but this is only sort of Friday. I'm not saying this is mandatory, but it's well worth having a go, seeing what you come up with, making the mistakes, going through the thought process, and I'm more than happy to go through some of these next lesson when we meet again. So brilliant. Well done for coming online, guys. Good to see you. And we will catch up Friday. Drop me a message if you're having any problems, if I've confused you with any of that, because actually that's quite difficult science, but it comes up on foundation and higher papers. So we do need to make sure that we've probably got our head around that. And please enjoy the rest of your day. It seems like it's almost sunny out there again. So take care.